Hello, good morning. Good morning, everyone.
Good morning.
Okay, let's start now. Okay. Right. So electric field and electric field lines we discussed now last class, right? Hello.
Yes, sir.
Yes, sir.
Yeah, electric field lines we discussed
Yes,
now
sir.
last thing in the class. Okay. So let, let me reduce the number of page otherwise. All the notes you are arranging it now. So let's continue with the electric field lines we discussed. Let's discuss about the electric flux now. Okay. So what is electric flux? Please tell me, what does it mean by electric flux? What is the meaning of electric flux? Tell me. Please tell me, what is electric flux?
Field line is passing through a certain area.
Yes. What is electric flux? It is the number of field lines passing through what? A cross section area is called as what? The electric flux. Okay. Is that clear? So electric flux means what? Electric flux means what? The number of field lines. Okay. Electric flux means what? It is the number of field lines. Okay. If there is
Yeah.
the tell me, it is the number of
Field line in
field lines passing through a given cross section area. Okay. Passing through a given cross section area. Okay. So what does it mean? Let's say there is a cross section area like this, and these are the field lines passing through it. Okay. So here, more the number of field lines will cross this cross section area, will pass through this cross section area, more we will call it as the electric flux. So if I want to calculate mathematically what is the electric flux, right? How to represent the electric flux? So can I say that electric flux will depend on what is the electric field in a region? It will also depend on what is the area through which we are trying to calculate the flux, isn't it? Because more the electric field strength, more will be the flux. More the area, more will be the flux. And one more thing, is the angle between the electric field and area vector also, isn't it? Because orientation also matter na, when we are calculating the flux. See that same area is there. See here in this question, this is the area, this is the electric field direction, this is the area. There will be flux, but same area and this is the field. See that same cross section area, I kept it into different orientation. Do we have different electric flux in these two cases? So that means what? Electric flux depends on electric field strength, it depends on area, and also it depends on the angle between the electric field and area vector. Okay. So area is what? Area is a vector quantity. Okay. So what will be the direction of area vector? Direction of area vector is always perpendicular to the surface area, and it is what? Outward direction. Means if I say this area vector, draw it, so this area vector will be what? Outward direction, like this. Okay, so area vector is always drawn in which direction? In the outward normal direction. Okay, so electric flux is given as what? Electric flux we represent it by the phi. Phi is given as what? E dot A. Now you will say, sir, this is the dot product, how do we take the dot product? So let me give you some idea about the dot product. Okay, are you clear about the dot product, or should we discuss? Because in the vector chapter we discuss only the addition, subtraction, and component thing. So should I discuss a little bit quickly about the dot product, or are you aware about the dot product? Then we can go directly with the questions.
No, sir. We know, sir.
Okay, everyone knows? Please tell me. Please tell me.
Yes, sir.
Lokesh and Charan, tell me. Both of you know about the dot product?
Sir,
Yes,
I
sir.
told sir already.
Okay, okay. Right. So let's take it now. So see, dot product of what? Electric field and what? Electric field and area vector, that is called as the flux. Okay. So if we want to calculate the flux, what we will need? We will need the electric field vector and we will need the area vector. Okay. And one important thing, what is the direction of area vector? The direction of area vector is what?
Perpendicular to.
Always perpendicular to the cross section. Okay. So just keep in mind, area vector is what? Area vector is always drawn as outward normal. Okay, outward normal to a given cross section area. मतलब any cross section area is given, a wall is given, or any surface is given, we should always draw the area vector as what? Normal to the surface area, and that normal should be what? Outward of that surface area. Okay, so area vector is always drawn as outward normal to the surface area. Is that clear? Up here, if electric field is constant, right? So what we can use it? If electric field is constant, we can write the flux equal to E dot A, or we can also write it magnitude of E vector, magnitude of A vector, and the cos theta. This is how we take the dot product of the two vector. If dot product of the two vector we want to find out, A dot B, so what we should do it? It is magnitude of vector A, magnitude of vector B into cos theta, where theta is the angle between the two vectors, right? Theta is what? Theta is the angle between the two vectors, and angle between two vector means what? Angle between their tail or between their head. Okay, angle between the two vectors are what? Angle between their tail or angle between their head is called as the angle between the two vectors. So if electric field is constant, then we can directly take the dot product to get the flux. But sometime it may be possible that electric field is variable in the question. Okay, so in that case what we should do it? So if electric field is variable in the question, okay, if electric field is variable, then what we should do it? Then first we should calculate a small electric flux, okay, E dot dA. Then first what we should do? We should calculate the small amount of electric flux. Small amount of electric flux means what? E dot dA. And then to get the total electric flux, what we should do it? We should, okay, that will give us what? The total electric flux. Okay. Now, for the electric flux, we follow some convention and that convention comes from the dot product only. Like if I say there is a cross section area, okay? So if electric field lines are entering a cross section area, for the cross section, to no problem. You can take it this also as your normal vector or this also a normal vector, and both will be the correct one. So we should always take it what? The normal vector in such a way that flux become positive if it is just a cross section. But if it is a closed surface, then we have the certain type of what? Certain type of area vector. Is that clear? Then we don't take it any random direction as the area vector. Is that clear? Let me take some example and we will understand then. Please tell, is this part clear?
Yes, sir.
Right. Let's see an example of flux calculation. In this example, what is given to us? A cube is given to us, okay? A cube is given to us. Okay, and this cube is given in such a way that this side is along x-axis, this side is along y-axis, and this side is along z-axis. Okay, so tell me, I'm going to ask you simple question. Tell me, if electric field is uniform, what will be flux through the cube? If electric field is uniform means what? Constant in magnitude and constant in direction. Then can you tell me what will be flux through the cube?
0.
Will it be 0? Please tell.
Yes.
Please tell me, is it going to come 0? If electric field is uniform, then flux will be coming how much? It will come 0. But if I give you electric field as variable, then also the flux will come 0.
Yes, sir.
If it is variable, then also it will come 0. Chale, let me take the two cases, okay? First case given to us, electric field as E naught I cap plus E naught J cap. And this is a cube of side what? A. Okay, this is what? A cube of side A. Okay, so now if I try to calculate the flux, how many faces are there? Let's just mark those faces: A, B, C, D, E, F, G, and H. So tell me, if I'm calculating the flux, tell me for ABCD, what will be the area vector for ABCD? See that for ABCD, sorry, for ABCD, what will be the area vector? Check it. Is the area vector will come in the plus J cap? Please tell. For ABCD, if I'm
Yes, sir.
calculating flux through ABCD, can we say that area vector is in the J cap? And what is the electric field? Electric field is E naught I cap plus E naught J cap. Area vector will be how much? What is the area? A cross A na? So A square J cap. Now you see, if you take the dot product, how much it will come? Dot product, how do we take the dot product? One method for taking the dot product is this, right? Mod A, mod B, component x I cap, y j cap plus, and the other is something A I cap and B C K cap. Take product component to this component x way will make y and b, so it will become z and c. That was what z into c, the component method. Okay, and dot product is what? A scalar product. Why? Because it is a dot product of two vector quantity whose resultant gives us what? Whose resultant gives us as a scalar quantity. Okay. So E dot A, if you do it, see that what you are getting? Are you getting I cap dot I cap? So that part is 0, isn't it? We don't have any I cap component in the area vector, plus E naught A square, that is the flux. Now, if you calculate the flux through EFGH, can you tell me what will happen? EF, look at that, EFGH. For this one,
We'll
what
get
will
the
be
same
area
but
vector? Yes, area vector is what? Always
towards
outward
the center.
and normal to the surface. Right? What is the direction of area vector? It will be always outward and normal to the surface. So for EFGH phase, can you say that here also the flux is same, but this time it is negative. Okay, E naught I cap plus E naught J cap is the field. And what is the area vector? The magnitude A square. But what is the direction of area vector? Minus J cap,
Minus J cap.
right? So now if I take the dot product again, I cap dot I cap, that part is not there. J cap, if I do it, so is it coming? Minus E naught A square. Please tell me. Same thing. Let's do it for what? Let's do it for the BCGF. Check it. BCGF. Can we get the answer now? What is the area vector for BCGF? Is the area vector is normal to BCGF and away from the
Plus
surface, outward from the surface. So what is the area
plus
vector?
I cap.
Plus I
SI.
cap. Understood? Plus I cap for this one, minus J cap, right? And same way, if you calculate it for ADHE, will it come minus I cap as the area vector? Please tell me. So if you calculate flux through B, C, G, F, which phase we are calculating? B, C, G, F. So how much it will come? It is what? It is the area vector is in the plus I cap, na? So how much it will come? Electric field E naught I cap plus E naught J cap. And what is the area vector? A square plus I cap. So how much is that coming? E naught A square. So how much it came? E naught A square. E naught and J cap component other side 0. So that's it. So if you calculate for, tell me what it will come. A D H E. How much it will come? Tell me. ADHE. What is the area vector? I am again going to represent it. Tell me. What is the area vector now? Is this the area vector? Normal to
Minus
the
I cap.
surface and outward, minus I cap. So
Yes,
again,
sir.
just write it E naught I cap plus E naught J cap into A square into minus I cap. We will write it. So what we have here? What we have? We are having minus E naught A square. Now, two more faces are there. Na? A cube had total 6 faces. Please tell me, what is the flux through the two more face? DCGH. DCGH, tell me. Is the electric field is
Plus K
in
cap.
the plus E naught I cap plus E naught J cap. And what is the area vector? Plus K cap.
Plus
So
K
A
cap.
square into K cap. Is that coming 0? Tell me,
Yes,
is
sir.
this
Again,
dot
we'll get
product is coming 0? Right? And same thing, there are one more phase, A, B, F, E, na? A, B, F plus E naught J cap dot A square minus K cap, that is coming 0. Can you tell me what is the net flux through this cube? Net all these flux through indivisible faces we have calculated. If I want to know the flux through the cube, what should we do? We should find out flux through these indivisible faces and then we should add it. And flux is a scalar quantity. So plus E naught square minus E naught square again plus E naught square minus E naught square. We have added and we got what? The net flux. Okay. So you know there is an important property about the electric flux. Whenever we calculate electric flux through a closed surface, please listen it carefully. Whenever we calculate electric flux through a closed surface kept in uniform electric field. Understand? Kept in what? Kept in a uniform electric field. Then net flux through the closed surface will be how much? It is always going to be what? 0. Please tell me what point I just said. Net electric flux. Please tell me, can you see that? Net electric flux through a closed surface. Okay, through what? A closed surface. But keep in mind the surface should be what? A closed one. Okay, now the shape of the uh, object through which I want to calculate the flux, that must be a closed surface. Okay, so net electric flux through a closed surface kept in a uniform electric field. And another condition is what? The field should be what? Uniform. In a uniform electric field is how much? Is 0. Please check. Understood this point? Net electric flux through a closed surface kept in what? Kept in a uniform electric field is what? 0. Are you clear about this one? Can you see that? The field is uniform. This field is uniform. Now check it. This is what kind of field? Uniform electric field. Because if you see that, there is no change in magnitude and there is no change in the direction. So that's why this is called what? Uniform electric field. So if you keep a closed surface in a uniform electric field, the net flux through the closed surface is always going to be what? 0. Is that clear? Now, second thing,
Yes, sir.
can you say that what is the direction of field? Can I say the direction of field is it is in the plus and it is in the plus j cap? That can I say if I feel like this is entering a closed surface, can we and feel line as what? It is, and if the field line is the closed surface, then can be happening because of the vector. Is that clear? See that this phase is negative, ADHE phase. It is entering this one, isn't it? What is the direction of field? Direction of field is E naught I cap and E naught J cap. Okay, this electric field given in the question is E naught I cap and E naught J cap. So see that is this I cap field lines are entering this shaded cross section. Check it. So that means whenever we have a uh, closed surface given to us, then the flux or field lines, okay, entering the closed surface gives us what? Negative flux, and the field lines exiting the closed surface gives us what? The positive flux. Is that clear? Please tell me. So can we write it here? For a closed surface, what we can say? For a closed surface, entering field line or entering flux, है ना? Entering field lines gives me what? The entering flux, okay? So entering field lines, or you call it is. And what about the exiting flux? And exiting field lines, okay, exiting field lines, or you can call it exiting flux is what? It is the positive. Is these 2 points clear? Please tell me.
Yes, sir.
Please tell, are these 2 points clear?
Yes, sir.
Hello?
Yes, sir. Clear.
Right. Okay, so let's continue. So do you understand these 2 points about the flux? What are the 2 points we have learned about the flux? That if we are calculating the flux through a closed surface and the field is what? Uniform. Keep in mind what is the field? The electric field is uniform. Then what will happen? That electric field will create how much? Net flux as zero flux. Okay, electric flux created by a uniform electric field is how much? Is zero. Check it. Yes. Just give me one moment, okay? Hello. Please check it. Is it audible?
Yes, sir. Yes, sir. It's audible.
Right. Okay. So net electric flux through a closed surface is how much? Zero. And for a closed surface, entering field lines we will consider it as what? Negative. And exiting field lines what we will consider? Exiting field lines we will consider them as positive. Is that clear? That is the second point we have learned. Now let's discuss an example here based on that. What does it mean by entering field lines, exiting field lines? Okay. So in this example, what is given to us? See, in this another example, it is given to us that a closed hemisphere is given to us. Okay. And it is kept in what? It is kept in a uniform electric field. What is the field? Field is uniform and its value is given as U naught. And the radius of this hemisphere is given as what? R. So now they are asking flux through find flux through the curved surface, not through the flat surface. Find the flux through what? The curved surface. How much flux the is going to be through the curved surface? Please tell me what we can write. Please tell. A uniform electric field is there in the region, and in that uniform electric field, a hemisphere is kept. Now they are asking in the question, what is the flux through the curved surface, not through the flat surface? Can you answer it? What we should do it here? Please tell me. Can I write it in this question? The net flux is going to be 0?
E naught pi r square.
Right. Yes. E naught into pi r square. Why? Because net flux is going to be 0, isn't it?
Sir, E naught
And
pi r square.
yes, that's the
Sir, E
correct.
naught pi r square, sir.
Yeah, that is what we have. E naught into pi r square. Correct one. Okay. So how do we got it? Net flux is 0. Can I say net flux will be the sum of flux through the flat surface and the curved surface? And that should come 0. A flat surface we can find out E naught into pi r square, and that will be negative. Why negative? Because through the flat surface field lines are entering. Through the flat surface what is happening? Field lines are entering. And through the curved surface it is what? Exiting. But the sum of these two field lines should be what? These two flux should be what? 0. So what is the flux through the curved surface? Please tell, is this part clear?
Yes, sir.
So
Yes, sir.
that's what we here, that whenever a field lines is uniform, whenever there is a uniform field lines in a situation, what we should do it? We should make net flux through any closed surface as what? As 0. Okay. Next, one more example. Let's see, in the question what is given, a cylinder is given to us. It's again a closed surface, isn't it? And this time the field lines are given like this. Okay. A cylinder has how many faces? Can you tell me? Cylinder has what? Three faces, na? Two flat face and one which face? One the curved face, isn't it?
One curved face.
One, yeah, and two flat face. Can you tell me what is the flux through the flat face? It's a uniform electric field. What is the flux through flat face? The circular face. How much will be the flux through the
Zero,
circular
sir.
face?
Zero.
And same thing,
Zero.
0. Flux through the flat face or flux through circular face. How much it will be? Can I say flux through the circular face is going to be 0? What is the reason? Because for that electric field and area vector has what? Become perpendicular. See that electric field direction is horizontal.
Parallel, sir.
Area vector will be vertical. Yes.
Perpendicular.
No. Electric field and area vector.
Yes, sir. Perpendicular.
Electric field and area vector is what? Parallel. Electric field plane is parallel to the area vector plane is parallel. Area vector is what? Perpendicular. Okay. The flux through the circular faces are 0. Now I am asking in the question, what is the flux entering through one of the curved faces? Okay. Understand the question?
E
Flux
naught 2RH,
entering.
sir.
Net flux to again going to be 0. Right now?
Sir, E
Yes.
naught 2RH.
Yes. E naught into 2RH. Flux entering through the curved surface if we want to calculate. Okay, entering through the curved surface will be, so what it will be, see that how many field lines entered. So does it depend on what is the projected area of this cylinder on the wall, right or not? And projected area, if you want to see that, what is the meaning of projected area? Meaning of projected area means just put a torch, put a flashlight and see how the shadow will look like on the wall. So on this wall, if you try to see the shadow, how the shadow of this cylinder will look like? Is the shadow of cylinder is looking like what? A rectangle, and rectangle of what area? 2r into h area. So that is called the flux through. That is called the projected area. Okay, the flux entering through the curved surface. Entering through the curved surface is going to be how much? E naught into, what is the area? The projected area 2RH. And it is entering flux now. So should I write it negative? Please tell me. Flux
Yes, sir.
entering through the curved surface can be written. it is negative. And flux exiting through curved surface, flux exiting through the curve surface, how much it is going to be? Can I write the same thing? But this time I will write it plus, na? Because it's exit flux. Na? Exit flux is positive. Entering flux is what? Negative. Please tell, is these things are clear about the flux calculation? So vector is given. Sometimes they will give you in the vector form, that electric field vector in the I cap, J cap, K cap is given. Area vector is also given in the I cap, J cap, K cap form. And then they are asking what is the flux. Let's take one more example like that. In the question given to us, electric field in the region is given as 2 I cap minus 3 J cap plus 6 K cap. And area vector is given as, it is a, how the area vector is given? Area vector is given, area vector is a square or is a rectangle in xy plane, okay, of 10 cross 6 meter square. What does it mean? Tell me. What is the flux they are asking in the question? Tell me, what does it mean by area vector is in xy plane? If you have a rectangle in xy plane, what will be area vector of that rectangular plane? What will be the area vector of the rectangular plane? If the plane is in xy plane, if the area is in xy plane, can I say the area vector will be in the z axis? So that means here in this example, what is the area vector? So in this example, the area vector is, what is the area? 60. And it is in xy plane. Na? Xy plane means what? Area vector is in the z axis. Z axis means which direction? Plus k cap. Now we want to calculate the flux. So if we want to calculate the flux, can I take the dot product now? So what is the electric field vector? 2 I cap minus 3 j cap plus 6 k cap dot 60 k cap. See that I cap is not there, so it becomes 0. J cap not there in the other one, 0. Only k cap with k cap will come. Na? So 6 into 60. How much it will become? 360. Can you tell me what is the unit of flux? Newton per coulomb meter square. Right now? Is it the unit of flux? Check it. Electric field unit will be what? Newton per
Newton per
coulomb. Na?
coulomb
What is the unit of
meter square.
electric field unit is Newton per coulomb, and area unit is what? Meter square. So overall unit of electric flux is what? The Newton meter square per coulomb, and it is a scalar quantity. That is another important point about the electric flux. Okay. Now let me take one last example on what? Let's take the variable electric field and try to calculate the flux, how much it will come. Okay. In this example, what is given? Electric field is given. I'm again going to draw a cuboidal shape. Okay. Cuboidal or cube shape, I am going to draw it. Okay. I want to calculate flux through this cube shape object, cube shape surface. Okay. This is the cube. This is x-axis given. This is y-axis given. And this is z-axis given. Here in the question, what is given? Electric field is given as E naught x I cap. What is given? E naught x I cap is given to us. Now they are asking again flux. Here in the question they are asking find flux through the cube. find flux through tube. Understood? So please tell me here, electric field is only in the I cap. So can I be sure that only the area vector which is in the I cap is going to give me the flux? Are you clear? Please tell me. So we don't need to calculate unnecessarily for all the phases. Please tell me. We don't need to calculate flux through all the phases unnecessarily. Why? Because electric field is in the I cap, right? So any area vector which is in the I cap is going to contribute for the flux. And for other vector, if area vector is in J cap, electric field is in the I cap, then the dot product is going to 0. So that's why we should focus on the area which is in which direction? It's in I cap direction. So can I represent those? A, B, C, D. Is it the A, B, C, D area through which I have to calculate the flux? And also, which other phase? Do I have to calculate the flux through this another phase? Please tell me. Flux through this another phase also we have to calculate it. Let's call it E, F, G, H. So please tell me what is the area vector for this one? Is the area vector for this one is plus I cap? What is the area vector for this one? Is the area vector for this one is minus I cap? So chaliye, let's calculate it. What is the flux through ABCD? The flux through ABCD, if I calculate it, what is the electric field at x equal to at this phase? When I'm going to reach this phase, what is the flux field there? Is the x value at that point is equal to A? Please tell me. When I am talking about the phase ABCD, is the electric field at that point is equal to x equal to A? So can I say that electric field here will be E naught into A I cap? Please tell. Because x value is equal to A. Because x value is equal to A. So E naught A I cap dot. What is the area vector? A square I cap. So what is the flux we are getting? E naught A cube, we got it. That is coming positive. And if you write the flux through E, F, Z, H, what is the electric field there? Please tell me, what is the electric field at that point? Where the phase EFGH is there? Please tell me, what is the electric field at the phase EFGH? Is the electric field there is itself 0? Please check it. Is the electric field at EFGH is itself 0? Why? Because at EFGH at this point, everywhere the x is 0, na? So that's why. And everywhere on the blue cross section is the x is equal to A. So here what happened? The field becomes 0. So that means if I take it area as A square minus I cap, still it will be 0. And what about the flux through other four phases? Is the flux through other four phases is always 0? Please check it. Is the flux through other four phases of this cube, is it 0? Why? Because other four phases are always electric field and area vector in the perpendicular direction. Because area electric field will be always in the I cap. If I talk about the ABFE phase, like this phase, ABFE phase, see that electric field I cap, area vector plus J cap. Dot product will become what? 0. Understood? So that's why other four phases we don't need to calculate. So can I say here the net flux is how much? E naught A cube only. These are the flux calculation method using what? The dot product, or using what? The dot product, or using some uh, if it is variable, then we will calculate it the small element, then we will write the flux. These things is what we have done it in this question. But there is another method to calculate the electric flux, and that method is called as the Gauss law. But for the Gauss law, there is one important point we need to understand, that Gauss law is only applicable for what? The closed surfaces. Okay. With the help of Gauss law, we are going to calculate the flux, okay? But here we are only going to apply for what kind of surface the flux calculation? Closed surface, okay? Like any closed surface is given to us. And this closed surface has some Q1 charge, some Q2 charge, some Q3 charge, and there are some charges outside as well. Q4, there is one charge here, Q5. But please keep in mind this surface within which the charge is kept is what kind of surface? This is a closed surface. Are you clear? This is what kind of surface? Closed surface. And this closed surface is also called as what? The Gaussian surface. What can be the shape and size of a Gaussian surface? It can be anything. Okay? There is no restriction on the shape and size of a Gaussian surface. It can be anything. It can be a cuboidal, it can be a cube, or it can be a spherical or cylindrical. So Gaussian surface can be of any shape and size, but it should be a closed one. That is the one necessary condition about the Gaussian surface. Okay. So now, as per the Gauss law, if you want to calculate, okay, as per the Gauss law, if we want to calculate net flux, net flux through any closed surface area, net flux through any closed surface area, what it will be? Net flux is going to be how much? It is going to be Q enclosed by epsilon naught. Q enclosed by what? Epsilon naught. What is Q enclosed? Please tell me, what is Q enclosed?
The
Q
charge is
enclosed
present
means
inside
what?
the circuit.
Yes. Q enclosed means what? It is the charge present. Okay. What is Q enclosed? It is the charge present inside the Gaussian surface. Okay. Charge present inside the Gaussian surface. Okay. So whenever we calculate flux through a Gaussian surface, what is important about the charge? So the important thing about the charge is what? What amount of charge is within the Gaussian surface? What charge is outside, that doesn't affect the flux. Clear? The charge which is lying outside the Gaussian surface doesn't contribute for what? The flux calculation. So sometimes they will ask you theoretically one thing. Total flux through a Gaussian surface depends on what? Inside charges, outside charges, or all the charges?
Inside charge.
Inside charges only. But in a region or in a space, if I want to calculate the electric field, will it be due to inside charges, outside charges, or due to all the charges?
Due to all the charges.
Right. So that's why field at a point is what? Due to all the charges present in the surrounding. But flux is only what? Due to enclosed charges or charges within the Gaussian surface. Is that clear? So here, if you write it, can I say if I want to write the flux through this Gaussian surface, the flux will only come because of what? Because of the Q1, Q2, and Q3, right? So here, can I write it? Here in this example, the net flux will be Q1 and charge is a scalar quantity. So Q1 plus Q2 plus Q3 divided by what? Epsilon. Okay. So the flux is going to only depend on what? The charges which is present within the Gaussian surface. Okay. This is what we have learned about the Gauss law. Is that clear? But one thing we have important is it should be a closed surface. Then only we will call it as the Gaussian surface. Okay. Not the open loop or something like that. Okay. It should be what? Always a closed surface. Okay. Now, the next thing we have is the once we know this one, right? Second thing about the Gauss law. First thing is what? It is for the closed surface. Now tell me, can we apply Gauss law for any kind of shape and any size of the surface? Please tell me. Gauss law is what? Can I say Gauss law is applicable for Gauss law is applicable for all type of shape and size of the surface. Please tell me shape and size of the Gaussian surface. Is that clear? So shape and size does not affect the outcome of the Gauss law or flux calculation. Okay, flux calculation only depend on the charges within. Meaning is what? Like if I say there is one question like this. This is a Gaussian surface, and there is another Gaussian surface like this. I kept two charges q1 and minus q2 here, and here also kept at iq1 and one charge minus q2 here. Can you tell me what will be flux through the Gaussian surface? This is the one Gaussian surface and this is the other Gaussian surface. Can you tell me both Gaussian surface will give me same flux or different flux?
Same flux.
Please tell me Gaussian surface, same flux. Does it depend on the shape? Please tell
No,
me.
sir.
Does the flux, can I say flux in the case 1 and flux in the case 2, both are same and that is equal to q1 plus minus q2 by epsilon naught. Have you see what are the things you have learned it in this one? Flux through the Gaussian surface did not depend on the shape, it did not depend on the size, and also it does not depend on where the charges is present in the Gaussian surface as long as it is within the Gaussian surface, right? See that? Here, two charges are present near, away, anywhere. And in the first and second case, did I just keep the charges at different location? But as long these charges are inside the Gaussian surface, does it affect our flux calculation? Yeah, field calculation will be different, but does it affect our flux calculation?
No, sir.
Okay, so that is what we have learned. Gauss law is applicable for all type of shape and size of the surface, size of the Gaussian surface. And another thing is what? As long the charges are inside the Gaussian surface, it should not go beyond the Gaussian surface, outside the Gaussian surface. As long the charges is inside the Gaussian surface, then what is the shape of Gaussian surface? What is the size of Gaussian surface? And what is the uh, placement of charge inside the Gaussian surface, isn't it? These things does not affect our flux calculation. Is that clear?
Yes.
Yes, sir.
Okay. So the next thing we have to discuss is the using Gauss theorem, we will calculate what? Electric field due to few things. What are the few things? Electric field due to point charge. What will be electric field due to the point charge? Please tell me. KQ by R square, isn't it?
Yes.
KQ by R square. So, and electric field due to infinite line charge, lambda by 2 pi epsilon naught R. So now, can I write it? Flux through a surface is, now how many ways I can calculate the flux? Now I can calculate flux through two methods. Either I will use E dot dA integration or I will use it Q enclosed by epsilon naught. This is going to help us in calculation of all the flux. So whenever I'm going to find the electric field, what I will do, I will make a Gaussian surface, calculate the flux through the Gaussian surface. One method will be integration method. Other method will be what? Finding what amount of charge is within the Gaussian surface. Okay. So please tell me, is this part clear?
Yes, sir.
Okay. So if you see that we have discussed almost all the topic of this your first unit, right? Check it.
Yes, sir.
You have this uh, topic list,
Yes, sir.
right? So you can check it except the uh, this one induction. Okay, so that we will discuss in detail how to charge a body little bit later. Okay, so you see what are the topics we have here, right? Charge, property of the charge we discussed. Then we discussed the Coulomb's law. Okay, what is the direction of electrostatic force, right? Attractive, repulsive, gravitational force, right? It is large scale, weaker, right? Electrostatic force is what? More stronger, but its distance is what? Range is what? Less. Electric polarization, permittivity, right? What is the permittivity, right? You see, conservation of electric charge. Okay, this process of charging, we will discuss it a little bit later because for that we need the potential concept. Then we discussed about the electric field. है ना? Electric field is a vector quantity, right? In electrostatic equilibrium outside a sphere. So this we will discuss with the help of what? Uh, Gauss law. Okay, you see, electric field, right? Given charge distribution. This is the many times we have all the type of we have discussed. No? See that only expect calculus to find electric field infinitely long, infinitely okay, infinitely long, uniformly charged wire, cylinder at a distance on the central axis, thin ring on the axis, semicircular arc or part of semicircular arc, finite wire or line at a point charge, line charge at a point collinear with the line charge, and along its perpendicular bisector. So everything about this one we have discussed, right? Please tell me, right?
Yes, sir.
Hello.
Yes, sir.
Right. Now we are in the electric flux. What is area vector? Okay. What is area vector? How to calculate the flux, positive flux, negative flux, then using the Gauss law. So this is the last topic we have it in that one. Okay. So using Gauss law, how we are going to calculate it. So please tell me, is this part clear or any confusion there till now what we have discussed?
No, sir.
Actually, let's meet it tomorrow. Tomorrow again, we will go back to the mechanics part now. So by next week, we will have the electric charge and field completed, and then we'll go to the electrostatic potential part. Second unit is that one, na? Electric potential energy, potential. Okay, that we'll discuss. Okay, so take care, everyone, and let's meet it tomorrow.
Thank you, sir.
Thank you so much. Take care. Okay, Sharon, take care then. Let's meet it tomorrow.